Hi. In this video, we'll be learning about data compression. So, as we've seen, there is a lot of data in the world. In fact, if Google alone were to put all of their data on punch cards, which are tiny little pieces of paper that can only hold about 80 characters, so if Google were to put all of their data on punch cards, the amount of punch cards would be able to cover New England to the point that Boston would be buried significantly deeper than it was during the last ice age. Now, luckily, Google's not putting all their data on punch cards. We have much more clever ways of storing data on hardware like disks and tapes and drives, but the hardware only goes so far. We really need a way to shrink down our digital information. We need a way to shrink down our data to take up less space. The hardware does a pretty good job. We're finding ways to pack bits into smaller and smaller areas of space, but really we need a software solution. And the solution here is data compression. So data compression is the process of encoding information using fewer bits than the original representation. So we've seen all of these ways to encode data using bits. We've seen the ASCII encoding for text, we've seen the RGB encoding scheme for colors and images, but these encoding schemes aren't really concerned with saving space. They aren't really concerned with using as few bits as possible. So what compression does is it takes this information, it takes these bits, and it compresses them down to encode the same information using fewer bits than the original representation. So this is how compression generally works. When we want to store our data, we will pass our data into a compression algorithm, a compression function, and that will compress the data to use less bits for storage. Then, when we want to view that data again, when we want to see the image or see the text, we will pass that compressed data into a decompression algorithm, a decompression function, and that will decompress that data and restore it back to its original state. So we see here that the original and the decompressed data are exactly the same. So when this is the case, when we're able to fully restore the original data, this is known as lossless compression. And this is incredible. There's algorithms out there that can take data and pack it down to almost half its original size and still recreate the original. It's really mind-blowing. So this is what's happening every time you're interacting with digital information. Movies, images, text, all that information you're viewing on your computer is compressed before it is stored or before it's sent. And this is in order to save space and make the whole process faster. So why exactly do we compress data? Well, one is to save storage space. Like we've seen, we have way too much data. We need to come up with clever ways to store it. We're not carrying around massive hard drives in our pockets. We have little phones. So we really need to use that storage space efficiently if we want to be able to access all of our data. But besides just storage, it also speeds up the time it takes to transmit data. A network, like the internet, can only handle so much data at once. So if we compress our data before we send it, then we'll be able to send a lot more information over the internet. And it'll take less time because we have less bits to send. And at a high level, we're really trading off storage, which is expensive and slow, for computation, which is cheap and fast. And what I mean by this is, in general, we're okay with using a lot of computation if it means that we don't have to use that much storage. Take your phone, for example. So your phone really doesn't have enough storage to carry around a 300 gigabyte raw movie file, for example. But if you want to carry that movie around on your phone, what you can do is compress it down to a 1 gigabyte file. Then when you want to watch the movie, your phone actually does have the computation power to decompress that 1 gigabyte file into a full movie. So we generally have a lot more computation power on our devices than we do storage. So we're trading off storage for computation. Now, how exactly do these compression algorithms work? So really the way all compression works is we simply find repeated patterns in the data, and we replace those patterns with a placeholder that is much smaller than the original data. For example, say we had an image that was just a massive blue square. We have 100 pixels of blue. Well, that's 100 pixels and 24 bits per pixel, RGB, making it 2400 bits, or 2.4 kilobits. But really, the whole image is blue, so we don't really need to store every single pixel. Instead, we can store one blue pixel, and then also store the amount of times that it needs to be repeated. So here we have one pixel, that's 24 bits, and then we also store the number of times to repeat 100 times, and that might be 32 bits. We put that together and you only have 56 bits, so we've compressed all that information, 2.4 kilobits, into 56 bits. Now this might seem like a silly example, because usually we have a lot more complex data than just a simple blue square, but you'd be surprised how much information is actually repeated in all of the images, movies, and text that we use. Let's look at an example of compressing text. So one algorithm for compressing text is known as run length encoding, and how this compression algorithm works is it takes each character in the original text and writes that character followed by a number of how many times that character is repeated to the compressed text. So for example, here I have a single H, so I will write H1 to the compressed version. I have one H, and that is followed by 6 A's. So rather than typing out all those 6 A's, I'll simply write an A and a 6 to the compressed file. Then we have another H again, so H1, and then we have 6 more A's, so I'll write A6. And this is it. This is our compressed file, and it is much smaller than the original. You see, in the original, we have 14 characters, and since we have 8 bits per character, that's 112 bits. In the compressed version, we only have 8 characters. With 8 bits per character, that's 64 bits. Now when we go to decompress, we need a decompression algorithm that reverses the process. So what we'll do is we will loop over the compressed version, and we will write out that given character that given number of times. So first off, I see an H1, so to decompress, we'll write an H, followed by an A6, so we'll write out 6 A's, followed by another H1, it's a single H, followed by another A6, so we'll write out 6 more A's. And we see that the decompressed version is exactly the same as the original. So this was a lossless compression algorithm. Now, how do we measure a compression algorithm? How do we know when an algorithm is doing a good job? Well, one common measurement is space savings. So space savings is a measure of how much smaller the compressed data is compared to the original. Now, the formula for space savings is 1 minus the size of the compressed file divided by the size of the original file multiplied by 100. And what we get is a percentage of size decrease. So for example, if we take the run length encoding example, the original was 112 bits and the compressed was 64 bits. So to calculate the space savings, we simply do 1 minus 64 compressed size divided by 112, the original size, multiply that by 100. We see that we actually have a 42.9% space savings. The compressed data is 42.9% smaller than the original. That's pretty good. That's saving a lot of space. Now, there are a lot of compression algorithms. Run-length encoding is just a single example. This is a huge field of computer science, is finding better and better algorithms to make data smaller. There's a lot of algorithms to choose from. And it turns out different algorithms work better with different types of data. For example, JPEG is a common image compression algorithm, whereas run-length encoding works really well with text that has many repeated characters. Now, one important thing is that the decompression algorithm used needs to match up with the compression algorithm used. It needs to reverse that process. So the way we keep track of this, the way we keep track of which algorithms we're using on which data, is with file extensions. So a given file extension tells the computer what algorithm to use to decompress the data. So .jpeg uses the JPEG compression algorithm. So when a computer sees a .jpeg, it knows that that file was compressed with the JPEG algorithm, so it will need to decompress that file with the same JPEG algorithm. So .jpeg, .zip, .tar, these are all examples of different compression algorithms that produce different file extensions. So let's see an example of what these file extensions look like on a real computer. So here I have a folder with two simple files. If I open up this charmander.txt file, I see that it's just a simple picture of Charmander, the Pokemon. And what I want to do is compress down this text file to take up less space. See that right now it's taking up 2 kilobytes of space. But if I simply right-click and say compress charmander.txt, what I get is a zip file. So my computer used the zip algorithm to produce a compressed file. You see this is a lot smaller. It's 597 bytes. Now, if I change this file extension to .jpeg, it's going to warn me. Let's go ahead and do it. Now, if I try to open this, my computer is going to try to decompress that file using the JPEG algorithm. If we try to do this, we see that it runs into trouble. It says it could not be opened. It's damaged. It doesn't recognize this file format. That's because it tried to use the wrong decompression algorithm. If we change this back to .zip, yes. Now we try to decompress it. It will successfully decompress. And what we get back is a decompressed version. If I open this up, we see it's exactly the same as the original. We see that the zip algorithm might actually not be good for all types of data. If I already have a compressed file, like a .jpeg, if I try to compress that with the zip algorithm, we actually see that it got bigger. That's because the zip algorithm is not good for JPEG files. It's great for TXT files, but not JPEGs. So we got to keep that in mind when we're deciding which compression algorithm to use. So that's an overview of compressing data. to be this new character that we're at in the string. And after we loop over the entire text, we should have our results. We can return the result. So let's implement all these. These steps. For var I equals 0, I is less than original dot length, I plus plus, we want to do all of this. So if we're at the first character, if I is 0, well then we need to update run char to do this character. So current run char is equal to original dot char at I. And the run length should be 1. So current run length equals 1. We've seen one character so far, and it has a current run length of 1. Otherwise, we're part of an existing run, so we need to update that existing run. Else, do all this. Grab the current character, say var current character is equal to original dot char at I. If it's equal to the run character, then we need to continue on this run. If current character is the same as the current run character, then we gotta keep that run going. Add on to the run length. Otherwise, the run's over. So we need to add this to the result. For example, we would add, we'd hit the H, so now the W run is over, so we're gonna add that W4. So add the current character, the W, and add the current run length. And now we gotta start off this new one. Now we should be looking at an H1. So update those. Current run character is equal to current character, and current run length is equal to 1. And let's return the result. And just for this, let's return the empty string for now. We'll implement that later. Let's see what we get. Try hello. Ooh, this is interesting. So worked for the H, worked for the E, worked for the 2 L's, but we don't see the O. So what's the problem there? So this is a classic example of the fence post problem. We did this algorithm for the entire string, but since the string ended, this else never actually ran. We got to the end of the string without the O run ever ending. So to end that O run and add the O to be compressed, we need to do that after the loop is over. So the loop is done, this current run is over, so result plus equals current run character and the current run length. Now, we try hello. Nice, we get the whole thing. We can try what? Perfect. Now we gotta decompress it. So to decompress, what we'll do is we simply need to loop over grab every 2 characters and write out the given character the given number of times. So we'll loop over the compressed text. We will grab the in groups of 2. We'll grab the character, grab the run length from the string, and then write out character that many times to the decompressed text result. And then return the result. So if we implement all these steps, this should work. So let's try that. Our result starts off as the empty string. We want to loop over the compressed text, so for var I equals 0, I is less than compressed text.length. And then we want to do it in groups of 2. We want to do all this. We want to do this in groups of 2 because we are processing 2 characters at a time. We process W4, then we process H1, then A6, and so on. So get the character. It's going to be compressed text at I. And then the run length. Well, the run length character is going to be the compressed text character at that index. Char at I plus 1, but we want the actual numeric value. So run length is equal to parse int of the character. So that we get it in numeric form. And then all we have to do is loop this many times and add this character to the result. So for var x equals 0, x is less than run length plus, we will add this character to the result. And return. Let's see if the decompression works. What? Look at that, success. The decompressed text is the same as the original. We're checking that right up here. Original text is equal to compressed success. So that is an example of compression algorithm. Now it's your turn to give it a try.